So it's a great pleasure for me to introduce today Alberto Speranzon from Lockheed Martin for our Aviate seminar series. Alberto got his PhD from KTH, Royal Institute of Technology in Sweden in 2006, upon which he spent time in United Technologies Research Center in Honeywell, and now he's the chief scientist for autonomous systems at Lockheed Martin. Since Lockheed Martin is one of our partners on the NASA ULI, so it's a great pleasure and honor for me, Alberto, today to host you for this seminar. You can get started. If I miss something important from your biography, my apologies. You can add those details yourself, okay?
Sounds good. Ahead. Yeah, thank you so much, Naira, for the invitation and the introduction. So yeah, I will speak a little bit about some of the work we're doing in Neuro-Symbolic, but applied to autonomous system in particular. And so this is some work we're doing both internally as well as in collaboration with some collaborators externally. I put here a couple of papers that get a little bit more in detail of some of the things I'll speak today. So, if you were to zoom out a little bit before we jump into the details, I'm part of the ATL, which is sort of the corporate labs for doing research for cutting across the entire business areas of Lockheed. And within the ATL, which is Advanced Technology Labs, I'm part of the TIL, that is Trusted Intelligent Lab. And our focus is, sort of the classical problems that probably everybody would expect a lab with that title be working on. So machine collaboration, multi-scale, multi-domain, scalability, and compositionality. I think maybe that is a little bit a new buzzwords about compositionality. I'm very, very interested about developing systems that have those properties. A lot of work on assurance. In fact, I have other colleagues working on that particular aspect. And how do we manage uncertainty, ambiguity? It's a lot big effort. So the talk kind of covers a little bit these three main topics, and so we can jump into the neuro-symbolic approach for the OODA loop, right? So we are familiar with one possible way to decompose an autonomous system into the classical four-step observe, orient, decide, and act. And we've been developing this kind of system for a long time. And of course, today there is a huge effort in integrating learning-based component into these systems. But we know that these learning-based components are black boxes in many ways and difficult to characterize their behavior. And so there is this sort of parallel effort in trying to marry more symbolic approaches with sub-symbolic abstractions. And why that is, a reasonable effort is because ultimately we're able to incorporate more symbolic prior. So as you can imagine, when you deploy autonomous system, you would like them to be working with human teams. And so the expectation is that they will follow doctrines and procedures as humans. One of the key advantage when you do take symbolic abstraction, you get a huge compression in the state action spaces, making scalability more possible. Because you take symbols and relation between symbols, these tend to be more interpretable in terms of representation, and they have a little bit more better chance to be analyzed formally, which is critical if you want to deploy a safety critical application. At the same time, the idea here is not to abandon learning-based components, right? It's actually to combine symbolic abstraction and sub-symbolic ones, so you can still take advantage of those capabilities. And the other part is because we are really focused on a symbol and especially the relation, you can get a compositional property out of this representations. So that's sort of some of the key reason why should we even bother to think about symbolic abstraction in the OODA loop. So I'll speak about two main part of the OODA loop, the orient and the decide, and in particular, how do we generate richer world model abstractions, and the planning, how do we plan using symbolic abstractions. So we'll start with the world models. So this is actually something that many of you probably are familiar about, some of the work that Luca from MIT has been doing. So this kind of joint work with him, looking at some specific aspect. So point is what we see here on the right-hand side, this complicated hierarchical representation of the world that forms, dynamic scene graph or 3D dynamic scene graph, in the sense that it represents the information about the 3D world that the agent is navigating in, and is generating this hierarchy of representation that goes from low-level unstructured data like a point cloud or images, all the way to high-level concept like objects or places, and also give semantics to this object. And the links that you see, they capture relations, right? So there are inclusion relation typically, but you could actually look at other type of relations. And so you have this hierarchy of abstractions that as you go down, they are very geometric, rich in geometry. As you go higher and higher, they are more just semantic. There is less and less geometry, but because they're coming from the bottom up, you can always ground these particular entities down in the ambient space, in the ground space. Now, the tricky part is that because we would like to use symbolic abstraction, they are obviously very interpretable, but they also generate a much more compressed representation. There is a little bit of a question of how do we bring that, right? So if you look at under the hood, a dynamic scene graph is using multiple DNN and graph neural network to generate abstraction of different layers. But we would like this abstraction to be organized according to something that we can call a spatial ontology, right? We would like to ensure that the relations and the type of concepts that are in this representation follow a formal model like a spatial ontology. And as we know, ontologies, are typically very painful to build, right? And so, if you look at the kind of spatial ontology that we are considering here, what you would like to find or to express are relation between low-level concept and high-level concepts, where there are some relation. As I mentioned in this particular work, we have just focused on the inclusion relation, but in general, can be other kind of relations. And so you get both the high level object and the low level the high level objects or concept and the low level concept, they are connected by this relation. And so in general, in this particular context, they form just a bipartite graph. And the question is, this is nice, but how do we generate this, right? We don't want to write them by hand. And so that is one piece initially that we have been working on, is how do we extract ontologies, spatial ontologies from language models, right? We don't want to write them by hand. And so we are going to query a language model to generate the ontology. Now, this is not the actual schema of the ontology, right? This is actually the knowledge graph represented by some given schema. We don't try to generate the full ontology. We're only looking at the relationship that are interested for our representation. So that kind of cuts down in terms of trying to generate very reusable ontology. We're not attempting to do that. We're just trying to generate the part of the ontology and the key relations that are important for the dynamic scene graph. So that is sort of a little bit different. That was attempted, decades ago in trying to create these highly reusable ontologies with all the issues of trying to do that. Now, how do we do this? We come out with two main approaches. One is querying the language model by just asking, let's see, my cursor here, by asking what low-level object may be found with a high-level object. So you can look at all the different combination, and you look at the log probability provided by the language model. A better approach that actually we got more reasonable results when you compare to what a human would judge to be good is actually asking a more general question where you ask, among a list of low-level concept objects, what are the most likely to distinguish a certain high-level object. So, this could be a list of objects that you find in an environment. Which one of these is most likely to distinguish a specific room? So if it was a bathroom, of course, a bathtub and a shower and so on would be the most distinguishing objects to find that. And so this enables us to connect low-level information in the scene graphs, like the object in a room, with high-level concepts, which in this case are rooms or could be regions if you are outdoor. And so this type of query seems to work the best when you're trying to get this kind of information out of the language model. And you can see that the kind of query are sort of structured based on the kind of information we are trying to get out. They are not arbitrary. They are very specific based on the type of information we are trying to use. So now the issue is that we can extract all this information from a language model. Of course, there are some issues with some hallucination potentially and so on. But one of the biggest problem is that an ontology ultimately is a set of predicates in description logic. And so now you are facing the problem of how do you encode these predicates in description logic in a way that is compatible with the sub-symbolic layers, right, with the deep network parts. So one approach that we have been sort of exploring is what is called LTN, Logic Tensor Network. There are other approaches to do this. They sort of follow some similar paths in terms of transforming, first order logic, like description logic, into via multi-value algebra, right? So fuzzy logics, but I would say they're a little bit more general. But in practice is, you're facing the problem of differentiability with description logic. So you're going to try to make your predicate differentiable by using a sort of a continuous, making the logic continuous and differentiable using multi-value algebra. And the interpretation of in the logic tensor network is specific about tensor, right? So variables, constants, and so on are all defined or interpreted as real value tensor, which makes this nice compatibility with the classical approach we use in machine learning, where everything is represented as a tensor. Connectives and so on are operating on tensor, and the predicates themselves, the functions, are practically parameterized by learnable parameters, right? You can implement in practice a predicate where the variables are a tensor, but they are parameterized, right? So you can actually learn the predicate. And so what happens then is that you get a large set of predicates which then become part of your cost function. And so practically the problem, the loss function becomes a satisfiability problem practically. Is a continuous version of it because we rely on multi-value algebra, so, and it's differentiable. And so, you're practically bringing together logic and machine learning in some sense by taking this representation. So then if we try to marry this approach to what we are trying to do, which is try to identify what are the high-level concepts, meaning in what room is the autonomous system or in which region of the world is the autonomous system in, from the object that we can detect as we navigate around the world, then we can now start using the ontology, which relates what are the most informative object to define a specific high-level concept, so region or room. And so the first thing we did was to generate what we call equivalence predicates. Practically, this is using the actual label. It's saying that if you have a label of an object of being a kitchen, then we can use that label by saying that that object is, or that high-level concept is, in fact, a kitchen and is related by this low-level concept. So this is pretty much the same as using a cross-entropy loss, but we have transformed it into a predicate. The second piece is the one that is using G-relation, right? It's not using the label, but is saying that the kitchen is a kitchen because we see a fridge and a stove. And so this is not using directly the label, but just the low-level concept and the relations with high-level concept. And so we have something that is checking that the low-level object is a valid object, and then is looking at how this is related through the relation R in the ontology to the high-level concept. And of course, we use a neural network to generate the right embeddings to make this possible. And so we get this kind of predicate, which are using the inclusion relations that has been defined by the ontology. And so ultimately what you get is a large set of equivalence predicates based on your label and a large set of inclusion predicates, which are taking advantage of this spatial relation between objects and the corresponding regions or rooms. And so what happened then is just this becomes sort of the set of predicates which you are now solving the satisfiability problem, right? So you're now, the loss function become this aggregation of all the satisfaction of all these differentiable predicates, since we are using multivariate algebra to express all these predicates. So now what is the advantage of trying to do this in this context is that we have a in practice, a nice degradation of performance as you're trying to push the limit of labeled data. So in practice, what we see here is that in green is the cross-entropy loss. That is what we typically would do if we were to train something like this. And as of course, as you go to just 0.1% of labeled data used to train the model, you get really, really bad performances. Whereas if you're using just the green one is the satisfiability based on the equivalence relation. As I mentioned, the equivalence is leveraging the label and is, you can really think about working as just a cross entropy. As you can see, the trend is the same, right? As the label decreases, there is not much you can do since you don't have enough examples. But if you were to combine the inclusion relations and the label, you can get much better performance. Of course, if you were to use exclusively the relation and no label data whatsoever, you have a constant performance that is independent on the amount of training data, and that is where this curve tends to, because as we're reducing the number of labels, of course, what you are left is just the relations. Of course, this is a kind of a complicated data set. As you can see, even in the using state-of-the-art cross-entropy, you don't get a very high accuracy in detecting in which room you may be. And these other two are actually outdoor examples where, you know, some labeling was not very easy, so the ground truth is not super perfect. But you see a similar trend where by incorporating both the label and the relation, you got a lot much better results, despite the fact that you're reducing the number of label considerably. And so in this case, actually, we had not a very good data set. There was a lot of struggle here to label what part of the environment you are. And of course, right now we are working on a closed vocabulary. We are extending this to open vocabulary and so on. So that should improve quite a bit, since here we had to sort of define certain things which may not be the most informative one. But you get a similar trend in the sense that as you decrease the labeled data. So in this case, as you can see, we are not performing better the cross entropy. So this is actually a data set where in practice the label were sufficient in some sense to detect the or classify which region you were in. It's a fairly small data set, so there is not a lot of complexity in some sense, and it was not very easy to label this. But in some sense, this captured this reasonable idea that, you know, we as human, we don't need billions of examples of a kitchen to decide if we are in a kitchen. We are able to decide that we are in a kitchen based on, say, the object that it contains. Of course, we probably use a little bit more than just that, but in practice, you know, you can even be told what that kitchen is and never been in a kitchen. As long as you're able to see the elements, the objects in a kitchen, you're able to infer that you're in a kitchen, which is sort of a very interesting thought. So ultimately, we were able to get away with you know, 1000x less data, and we got graceful degradation of performance. Now, the one thing that we haven't done, and I think would be worth to do, is that the kind of object or let's say rooms that, for example, we kept label, we mask labels, so we remove labels from, are a bit of a variety of set of rooms, right? There is a bathroom, which is a highly distinguishable room compared to a living room and a family room, right? If we were even to try to discuss what is the difference between a living room and a family room, we'll probably need to argue for a bit, right? But a bathroom, a bedroom, really very distinctive, right? And so you can imagine actually to get if you were to only mask or only focus on the performance of the model over this very specific type of rooms, you would get performance that stay way high above. And of course, you will struggle a lot with living room and family as you reduce the number of labels. So that kind of brings an interesting challenge, right? It seems to be sometimes that there is almost like two camps, right? There is the machine learning, where data is the religion, give me more data, better data. And then there are the Neuro-Symbolic, which say, no, I don't want data, or I want little data, I just want to use the symbolic part. But the truth, I think, is something that is a little bit more in the middle, right? As I sort of argued in the previous slide, some concept like a bathroom, a bedroom, you know, a parking lot if you are outside and so on, they're very distinctive regions. And in those cases, I actually can rely more on the symbolic knowledge than actual data. But there are other concepts, other regions like a living room and a family room that they are really hard to identify you know, from just this inclusion relations. And there is a little bit more the style, you know, some of the way that things are placed that are much harder to define symbolically. For those, I want more data. So there is a little bit of a question mark, you know, given a problem, a perception problem, how do we define things that we can detect, classify with where we need more data versus things where we can get away with just symbolic knowledge. I don't think we have an answer to that. Right now it feels like we are just in two camps. Give me more data or just give me more symbolic information. But you can imagine that to try to symbolically define what a living room is compared to a family room, it's not going to be easy. And you probably need higher order type of relations where now you're looking at where that room is in the bigger, say, apartment or or region if you're outdoor, to try to define what that is, right? And you cannot just define this exclusively from the object that it contains. So that is an interesting question: is what do we want to encode as symbolic knowledge versus how much do we want instead to collect data, example. Now, another interesting aspect that I think is quite it's kind of overlooked in many of these things is that a logic tensor network practically is using these logical relations as a loss function, right? But once you have trained the model, you throw it away as we typically do and just use the model trained to do the classification. But in reality, you could still compute the loss function in practice, the value of this predicate during runtime, right? At runtime, and because they have this nice interpretation of being logic relations between different objects, we could actually use them to monitor what we are doing, right? The question is, how do you use this? What the role does it take, and so on. Now, another more complicated aspect of this, which I am quite interested about, and I haven't found too much done, is that, as always, right, multi-value algebra actually has very, very deep mathematical foundation in residuated lattices. But typically what happens is that you have the nicest lattice, which is the Boolean one, and then you start removing properties and you go down in the scale of nicely behaved lattices, and you get all the different type of multi-value algebra out there. And of course, if we want to retain this logic tensor network to be executed during runtime to sort of monitor what is happening, the reason why you want to do is that you would like to be able to reason at runtime about a part of the knowledge that you did not incorporate as you were training the models. So practically, you would like to do reasoning by combining what you see from the perception that has been trained with these predicates, but also from some other kind of knowledge. And now you have these issues that if you're working on a lattice where you remove all the nice property, now the reasoning becomes much harder. On the other hand, the reason why tendentially people use logics, multi-value logics, which are very deprived of property, is because it turns out that you have backprop issues, right? If you use the more constrained logic with a lot of property, it seems that sometimes backprop does not converge. So you have this very interesting question about that. On one side, you're trying to make the logic as weak as possible, and it seems to be that comes from the backprop. On the other side, you would like to retain the most stringent properties so that the reasoning becomes simpler during runtime. And there is a tension there, I think, that hasn't been really investigated sufficiently. So the other part is that, yeah, I think that is what I mentioned. Probably I should have clicked already here, but really this contention between the two. And in fact, in the original paper of Logic Tensor Network, in the appendix, the author actually come up with some very weird operators for the logic, which are not grounded in any strong mathematical property. They kind of behave as you would like in terms of and or, but they work really well in the backprop. But you have completely destroyed the property of the logic by doing that. And so what are the trade-offs are unclear. Of course, if all the focus is just incorporating logic predicates in the loss function, and then you throw everything away, just use the neural network. Of course, in that case, you're not really trying to do reasoning. So then maybe it's fine to just focus on the backprop. But I think there is some more opportunity here that should be and could be explored. I'm checking the time. Okay. So the other piece is a little bit about planning using relational abstraction. So there is a big interest about large-scale multi-domain and multi-agent missions at Lockheed, and the typical problem is scalability. How do we scale when you have this kind of complex decision problems? You would like to have compositional designs paradigm, and also assurance become a critical piece of the puzzle. And the other piece that I mentioned is that you would like this system to sort of be, according to some operational requirements, some mission rules. So you have all this symbolic knowledge that comes from the way that we approach this kind of mission that you would like to become part of your decision space. And the interpretability is not something I focus too much myself, but as I mentioned before, that is really a mandate in the sense of our team to not only try to do something that is trustworthy, but also trusted. And so how do we generate something that is interpretable becomes important. Now, there is a little bit of a question on how level should these things be interpretable. Do you need to know what my agent is going to be in the next 5 seconds? Probably not, right? We want something that is at least at the mission level, right? We're able to interpret. Maybe we don't need to know what the agent is going to do in the next 5 seconds exactly, but at least at the strategic level, what is the system trying to do? Now, we know that multi-agent reinforcement learning and decision making grows exponentially as the size of the space become larger. And the other aspect that is complicated is that we are considering different type of capability for each of the agents. So we want to ensure that we're able to capture all the different type of sensor capability, the type of platforms, and so on in the decision making. And of course, end-to-end solution, they typically don't scale too well. You need a lot of data. There are issues when things change that you need to retrain. Of course, you need very large scale simulation to try to do anything like this. And of course, in the kind of environment that we tend to work in, there is not a lot of data. So the idea is to sort of rely on the classical approach of decomposing the decision problems into layers. And the focus is a little bit more on the high-level decision making, and try to formulate this hierarchy of planning more as a hierarchy of neuro-symbolic abstractions. The level I tend to work nowadays tend to be more at this level, just because low-level decisions and if you go down all the way to the feedback control tend to be already designed by others. And so the question becomes more about, okay, now that we have this autonomous agent able to do all this different type of behavior, which behavior should we trigger when? And so that becomes this problem. Now, the thing that maybe, since I think the audience here is more with a background in control, maybe it's less surprising, but I think we tend to be very focused on the boxes of what goes into the boxes, rather than being more focused on the maps between these things, right? So if you design a high-level decision-making that has no refinable into a sequence of low-level decisions, then you are not going to solve the mission, right? If the system say, okay, try to go to A, but A is never reachable, then it's pointless to have this kind of high-level decision. By vice versa, if the state that the low-level decision maker is ending up has no representation upstairs, then this is never going to be aware that something happened downstairs, and it will continue asking to do the same thing, and this will continuously fail. So there needs to be more attention about these maps rather than the boxes, because it's easy to come up with the boxes, but then you get into this very big problem of having these things not really commuting, right? Not working correctly. So the approach that we took is trying to put all these different aspects together. And the approach that we've been sort of investigating is relational MDP. So it's using a relational abstraction. So it's lifting the decision problem to a new space, which is a space of logic predicates, where the actions you can really think about being changes in the truth value of this predicate. So this actually is sort of, in some sense, old-fashioned AI, right? Where, people used to create all this set of predicates and formalize them, and then learn policies over this lifted abstractions. And so we go from, the ground, the ground set of, state by using a set of description logic predicate into a representation where the truth values of the predicates are the state, and the action or transition between these truth values. Now, what you can do once you have generated a relational abstraction is actually you can use machine learning to learn policies over that, right? So that's actually a paper that sort of inspired us initially, is that you can learn policies by just using classical machine learning approaches, but over the abstractions. And it has a bunch of interesting benefit to do this. So, practically what you do is that you're sort of lifting, the capability of what the agent can do, and you are then, practically for a single agent, you are issuing sort of command at that level that are just truth predicate, a truth of high-level predicates. And then you can also exploit the relation between different agents by modeling relations as logic predicate. So what does this all mean? So the idea then is that we are able to abstract low-level behavior, as I mentioned, that arrow about abstractions, is that we are able to model them as a set of precondition and effects, right? And so these are logic statement that tells me under what conditions that particular behavior can be executed and what will be the effect. At some level, if you're familiar with semi-Markov decision processes or options in reinforcement learning, that's pretty much what this is modeling, right? You enter into behavior when these conditions are true. It will, after some stochastic amount of time, you will reach the end, the post-condition, the effects, and you will exit that behavior. And so this is a nice way to glue high-level decision-making with low-level behavior, but also because it is very formal in the way that it is set up, we actually have ways to now guarantee that the sequence of high-level behavior can be executed, and vice versa. If there are some conditions that we have not incorporated into our precondition effects, we can analyze the system in if the sequence of low-level behavior leads to what we want. So there are multiple properties that seems to be hitting the right boxes: assurability, scalability. There is interpretability, which then leads to more trustworthiness and trust. And it's certainly compositional, because now, practically, if you're looking at a sequence of low-level behavior, you need to have precondition effects that are well composed to get into the overall plan. But you also have this hierarchy that needs to be composable, where when the effects and the precondition need to be what the high-level decision making is using to make decision about what behavior to trigger. So ultimately, what you end up with is something that is way more compressed in terms of the abstraction. Of course, there is the downside is that you need to develop those abstractions. But once you're able to do that, then you're planning on a high-level decision space. And the other interesting part is that in principle, you don't need to hook up a low-level simulator to train a policy on the abstract space. Since we have all this set of predicates and the action or transition between predicates, in principle, you can look at all possibilities based on your reward function and find a policy upstairs that match the goals. Now, it could be that there are some transition here that will never happen downstairs, right? But those are things that practically, since it will never happen, they carry no real meaning. And so you can learn what to do in a certain case, even though that case will never happen. But that enables you to sort of able to train this part, or at least bootstrap this part without running millions of simulation downstairs. And another way to think about this problem is a little bit how we human probably try to do this, right? One way is that you could try to grid the space. So you say, okay, I take a grid and I discretize my problem, and I reason at a high level by just looking at the state of the agent in every cell, and then I say, okay, go to this other cell, and that will correspond to very complicated low-level decisions. That's one way to do it. But what is the grid? How should the grid be designed? How dense or not dense should this be? Rather than thinking that way, let's make kind of the discretization more task-oriented, right? So, for example, we may want to be aware of how far, there may be a region within which, we go from tracking the front of the fire to now a decision of where to drop the water, right? And that is maybe something that depends on where you are with respect to the front of the fire. So really the condition that triggers going from tracking where the front of the fire is to dropping the bucket of water really is just a spatial relation, a predicate about your distance to the front. So now the discretization is kind of became dynamic, right? And we only need reason about these things. So it becomes much more adapted to the problem, and so in general much smaller. Of course, there are issues, right, about uncertainty. What if you cannot detect the front very well, and so on? So there are certainly issues, and we are working on some extension when these predicates maybe are dependent on variables that are uncertain. Not just you just don't know the true the exact value. That's a way to think about it. And so here I have a cartoon that kind of shows, right, where practically this is your relational Markov decision. I'm not going to go through all the different things, but you have some stuff that is true, that needs to be true for the agent to enter the area of responsibility, and some other things will be false. So just think about this to be practically a state of your Markov decision process. And the action is going to sort of change the true value of some predicates. And so you can enter, and once you enter into the search, now you are changing the state of one predicates, which is big inside of this. And as the mission continues, practically you see this truth value changes as things change. But as I said, we are reasoning about the precondition of the actions, which are defined by the capability of what this agent. So if it has, for example, something that is tried to localize a set of people that is in distress to maybe launch a medkit, then we need to have that as a precondition to the behavior. And the other interesting part is that going through here without getting into the small details, you can also consider situation where maybe the UAV1 was supposed to drop a medkit, but now we are tracking, not every single medkit that a agent has, but maybe the boundary between when you have not enough and when you have enough, right? And so in this case, the UAV1 already dropped the medkit for the group 1, so it doesn't have enough medkits to drop for this. And so here you have a situation where you're now switching from the UAV1 trying to drop the medkit to the UAV2. So you can also practically capture at that level relations between the different agents and how should they coordinate. Now, there is another interesting aspect about this. As I mentioned, we are lifting the problem into this relational abstraction. We are generating actions by learning using machine learning approaches. And so now, because we have precondition, not all action can be executed from a given state, right? And so if you take a state, then you have a neural network that is approximating the Q function of your decision process. What you should do typically is that you have your state, you generate all the possible Q value for all the possible actions, and then you say, oh, look, action 2 has preconditions that are not satisfied, so I will cancel this and not execute it. Now, this is fine because we are sort of removing that, but we are spending time computing this, and we are not guaranteed that there will be an action that is satisfying the precondition. So a better way to do this is actually to preemptively shield the actions that are not available. So practically in this context, what we are doing is that we are generating a neural network for each possible action. So the price that you pay is that you have a more neural network than instead of a single one. But each of them is going to be smaller because we're only trying to predict the Q function. Oh, here there is some misspell, so this should be just A1 and A3. Just a single network that is predicting the Q value for the state and the action 1. And now, which network are we running are only the one for which the action precondition are satisfied. So now we are guaranteed that we will never run a network and generate the Q value for an action that from that state cannot be executed. So now you have an additive benefit that you are 100% guaranteed that you will never choose an action that is incorrectly triggerable from that state. So now, there is a little bit, more philosophical questions, right? In some sense, I showed this hierarchy of abstractions with this precondition and postcondition as a way to try to better design these refinement abstractions maps to have better compositionality overall of the system. But in some sense, I throw there an architecture with 3 layers and told to you that this is a way to do it. But there is a little bit about the question of what is a good architecture. Is that the right architecture, right? Usually, the way that we tend to design autonomous system, we start from a bunch of requirements, but right now we are just using sort of historical decomposition, right? So this 3-layer decomposition seems to make a lot of sense. Why? Because we've been using in the past with a lot of successes. Of course, now there are maybe more layers. What is inside each layer is maybe more complicated, but ultimately, this decomposition are driven by what we learned in the past. Now, that doesn't mean that is wrong, of course, but it is also true that this historical decomposition were somewhat biased by the fact that we had humans, right, part of the automation, not so much autonomy, right? And so there is a little bit of a question if we now think about this much more autonomous system that are supposed to take or at least have graceful degradation in the most complicated setting, is that the right architecture? Should this be 3 layers? How should the architecture of the perception match or not match the one of the decision making? So these are sort of open questions. I think that would be interesting to better explore as we now have this type of tools that enable us to speak about sub-symbolic abstraction with symbolic abstraction and so on. So now we can think about a little bit more if we are thinking the decomposition to be the correct one. So ultimately, this part of the talk on the planning, really the message is that, you know, instead of thinking about the problem on the ground space, right, on the ambient space where we have usual, you know, orientation, position, velocities, and so on and so forth, and try to learn a policy from this space, which is very, very large, especially grows exponentially as the number of agents increases. Maybe a better way is to really leverage this neuro-symbolic abstraction where we can learn models over this logical representation but do that in a way where our refinement abstraction maps are well designed, right? This precondition, postcondition are meant to try to enforce those maps to well behave well. So last slide. So conclusion, I mean, I do think that, you know, this neuro-symbolic architecture do provide some interesting opportunity on how to design trustworthy autonomous system, probably also trusted autonomous system, although I have not really focused too much on trust, but more on trustworthiness. But, you know, there are a lot of questions about, you know, how to do this, right? Knowledge capture is complicated. And so how do you mitigate that? Language models seem to provide a reasonable approach to that, but they come with a lot of issues, right? A lot of complications. So there is a little bit of a question about that. Should we try to symbolize everything? I don't think so. But how do we decide what to symbolize and what to keep data for or go get more data? Not clear. Compositionality, interpretability, and reusability of this is sort of obvious, but how do we, you know, unlock this in a much more you know, fundamental way, right, where we understand the mechanics and the principles to do this? Is right now it's more like point, right? We have evidence here and there, but we don't have a theory that really suggests how to do this. I haven't spoke at all about uncertainty ambiguity. It's really complicated now. You know, if you have to try to compute a precondition that depend on variables that are uncertain, what are we going to do about it, right? We're not, you know, without, probably it's not good to have just a true or false value. So how do you manage that? That's a good and interesting question. Of course, you know, Bayesian logic has a lot of complexity in terms of tractability. So we're trying to do some work in that direction, but certainly very complicated. And as I said, you know, one appealing point of neuro-symbolic is this possibility of, you know, using formal methods and so on. But I think it's an open question of how to exactly exploit that, right? We have more of a feeling. There are some, you know, some initial approaches, but I don't think there is a well-established understanding of how to exactly take advantage of this kind of architecture. So with that, I hope I haven't, 5 minutes. So I think we are decent time. So happy to take questions or comments.
Thank you, Alberto. It was great. Let's see the questions from the audience first. Just go ahead if you have a question.
Hi, Alberto. Nice presentation. I got a better sense of your neuro-symbolic framework. I had two main questions, and these are mostly broad. The first one is with the first part of your talk. I saw these predicates are conditioned on the relationships, what the spatial ontology has learned, right? It is only good as what the relationships have been learned. So is there a way to make that robust? But I can also think if they are robust enough, would you even need the predicates?
So the ontology, in some sense, you know, typically the way that you know, being description logic, right? Two things are in relation. You know, it's a true or false statement.
Yeah.
But when you take this sort of multi-value logic approach, you are kind of relaxing, in some sense, what that statement says, right? Is now you have a value between 0 and 1 about that predicate to be true or false. So even though there could be some kitchen that do not have a stove and a fridge, which would violate that relation, in reality, that is less of a concern because we're trying to find the maximum satisfiability over an interval between 0 and 1, in which sense, you know, some of the predicate could be in practice violated or slightly violated or not completely true, right? Because we have this a little bit of a slack in some sense. Now, the bad part of that is that, what is the interpretation of these numbers? It's not a probability, right? It's kind of a confidence, right? But in some sense, you can get away in some, by the fact that not everything needs to satisfy the relationships.
I see.
So you can do that.
I see.
Yeah.
So it adds like a layer of robustness.
That's right. That's right. There is a good question of, if you ask me how much robustness, what, how many, what if you put a relation that is most of the time false, right? Because you made a mistake or the language model made a mistake, right? That's a good question, right? We don't have a good understanding of how much robustness you can get and what happens if you put a lot of spurious relation that shouldn't be there, right? Will we be able to do that? That's a good question. I do not have a good answer for, but that certainly is an interesting question. I think that, especially the control community that I come from, when I saw this logic tensor network and the fact that they were relying on fuzzy logic was, I don't know, I'm a little bit but then I learned actually that fuzzy logic and multi-value algebra are much, much more grounded in mathematics than I ever thought. And the theory of residuated lattices may enable us to bring more of the mathematical principle back into these approaches and try to get a better understanding of the trade-offs, right, between the different choices. What does it mean when you have things that are maybe uncertain and you have probabilities, and what does this 0.5 numbers means, right? So, but yeah, this is certainly an open question.
Okay. The second question was, I saw that this was for the planning part. You have to still specify these precondition and the post-condition effects, right, for a given mission. So I need to encode this a priori before going into the mission, that there might be humans who might need rescuing, who might need medical kits, and so on, and the condition and the post conditions of that. So would it be beneficial to use these spatial ontologies trained offline to generate these pre and post conditions and dynamically shrink or expand this relationship abstraction? Because that's what I think humans do. Need not be that I need to encode this earlier, but in practice, I know it. And so I need to act.
Yeah, so just one clarification. The precondition and the effect or postcondition are really about the behavior, right? They're not about the mission. The mission then is the goal, right? So just think about that. I'm developing a bunch of low-level algorithms that are able to do search or able to do tracking, all the kind of things that typically we are interested. And I'm asking you that you're developing that to tell me under what condition your search should be triggered and what do you give me as a guarantee, a post-condition. It's almost like a contract-based design approach to where you say, I don't care about if you under the hood, you use some ergodic search, if you use, random search, I don't care. But the precondition are this and the postcondition are this, right? So this is fixed. For any problem, right, I can always keep this library of behavior that are all abstracted with precondition and postcondition.
So then there is the design level.
Yeah. Okay. And so now, of course, unfortunately, very often we don't design this behavior thinking about what are the precondition and postcondition. We design something and we claim that it works without fully understanding under all condition it does. So there are complications there. And of course, if you cannot characterize all the precondition and postcondition and so on, there are other kind of things that you need to do. But that is different than the mission, right? The mission goal then is a predicate or a set of predicates defined. When do you arrive a state that we would consider the goal state? That is sort of a different thing, right? That is what you are optimizing your reward, which is selecting all these different low-level actions, right? This behavior that satisfy the precondition, but you can change the goal, the mission in practice, and still have the same library of behavior, but the policy will change. You will need to retrain, right? But that's the way to think about it. I don't know if that helps.
Okay, yeah, that clarifies a lot. Thanks a lot.
Sure.
So thanks, Alberto, for the interesting presentation. I also have a question regarding 3D scene graphs.
Yep.
So I believe that using 3D scene graphs, you can have very detailed models of the environment because of the hierarchy and the different layers. But from a control perspective, I imagine that the controllers and the planners will be very overwhelmed with the amount of information provided by the 3D scene graph. So is there any way to extract the relevant information of a mission and to keep adding and removing objects online? Is this possible?
Yeah, so certainly you can, that is sort of a nice property of dynamic scene graph because you have a hierarchy of abstraction, right? You can always sort of threshold at some level of abstraction, right? I think the better way to think about it is, and I didn't connect the two too much since we ourselves are still working on that, but you can think about the precondition where the agent must be, say, in a parking lot before we can start the mission. So because the precondition is defined based on a concept at a certain level of abstraction, really, I don't need to know all the details about the parking lot as long as I can decide that I'm in a parking lot. How do I arrive to that conclusion is because I saw all the different objects in the parking lot and made me conclude. But at that point, in practice, the planner is only accessing the information about the high-level concept, which is, right, it could be a lower level concept that not only I'm in a parking lot, but I also need to be near a car. Okay, now, we need to go one level deeper, right? But you can imagine that in practice, the variables that this precondition depend on are happening at different level of abstraction in my hierarchy. So I don't need to, the planner does not need to reason about the entire world model, just need to reason based on the variables that its precondition depends on. So this kind of mitigates the problem of, should the planner now reason about this entire data structure? No, it doesn't, right? It can actually just focus on what the precondition are. And some of the precondition can have variables that are really, really deep into the ground state, right? Where I'm looking, okay, I need to be oriented looking north. So in that case, you need to go and retrieve that. And it could be something that has higher level information, like being in a parking lot.
Okay, yeah, thank you. And one final question regarding spatial ontologies. You mentioned two methods, like the text scoring and text completion. Is there one better than the other, or?
Yeah, the text completion was the one. Somehow my slides stopped. So why? I don't know if we have a good sense, but this one where we gave options to the language model instead of looking at all the possible pairs seemed to provide a spatial ontology that, if you were to look at it as a human, you would consider it more accurate. So that is a little bit of a open problem of how do you ensure, what is the right way to query language model and so on. So there is some work that we're doing internally to try to better understand that, and not only that, but try to carry uncertainty, right? As always, language model tells you something always with 100% confidence. There are ways that you can try to extract some level of uncertainty, which can then be incorporated into your satisfiability approach as well. But yeah, this seems to be working well, but would I be able to argue why? I don't.
Is it because you are giving more information to the language model?
That seems to be the case.
Just a yes/no question. You are giving a list of items. Okay.
Yes, exactly. That seems to be the reason why this seems to work better. But yeah, more than that, I don't think we have a good sense.
Okay. Okay, perfect. Okay, thank you very much.
Sure.
More questions? So if no more questions, let's thank Alberto for the interesting seminar.